Hello everyone. This is the last lecture of course PE 500, lecture 10. In this lecture, we need to solve two bioengineering examples and collect what we have learned throughout the previous lectures, such as the numerical methods, bifurcations, and the stability analysis. So let's begin. In the first example, we need to work with the gene regulatory network or GRN or the Hill equation. And again, the Hill equation is a common model for GRN as it describes how the concentration of a gene product, such as protein or mRNA, it changes over the time due to the production and degradation with feedback regulation. And we are going to deal with this equation. dg by dt equals beta multiplied by g raised to the power of n over k raised to the power of n plus j raised to the power of n minus gamma multiplied by g, where g is the concentration of the gene product, such as a protein again, beta is the maximum production rate, k is the half maximal effective concentration or the activation threshold, n is the Hill coefficient and it measures how sharply the gene responds, gamma is the degradation or dilution rate, and this is the nonlinear system. This is because we have here a power n. And this current example demonstrates how nonlinear dynamics are critical for modeling biological processes such as gene expression regulation. For nonlinear systems, we have mentioned that we can use numerical analysis and solutions to solve them. Also, we can use stability analysis to analyze the system stability and know the correspondence based on the initial condition and parameters. Also, we highlighted the importance of understanding the bifurcations and chaos. So we need, in this example, to simulate and analyze the system's behavior under varying parameters, focusing on the equilibrium points, stability, and bifurcations. So we are going to combine what we have learned into this example. So, as we mentioned, we have a nonlinear system. So we can use Roncote-4 or RK4 method to numerically solve the Hill equation over time, and this will provide insights into how the gene product concentrations evolve dynamically. And also, we will determine the stability of the equilibrium points, classifying them as stable or unstable. Also, we will construct bifurcation diagrams by systematically varying parameters such as the Hill coefficient n or the half maximal effective concentration k, and this will reveal how changes in these parameters lead to qualitative shifts in the system behavior, including the emergence of new stable states or transitions to instability. Combining all of that together will help us understand the GRN or the Hill equation model. So let's begin by solving the system using the RK4 method. In the RK4 method, we use 4 evaluations of the derivative per step to compute a weighted average slope, giving it high accuracy. And we compared RK4 with 2 other methods in a previous lecture. You can return to that lecture to understand what are the different methods to solve the differential equation numerically and compare between them. And by the end of that lecture, we emphasize that RK4 is the most accurate compared to them, and it includes these 4 evaluations, K1 to K4, where H is the step size and F is the function. And after calculating K1 to K4, we inject these coefficients or parameters into that equation, aiming to update and get the new value for y, given that we have the initial value of y. The second step is to check bifurcations, and simply bifurcations occur when small changes in a parameter lead to qualitative changes in the system behavior. And here we have 4 key parameters, nk, beta, and gamma. And by changing one or more of them, we will understand what are the constraints or limitations that can lead the system to transit from stable to unstable. So simply the steps here is to vary a parameter. For example, let's get a parameter such as gamma and simulate the system for different values. Find the equilibrium points by solving dx by dt equals 0 for each parameter value, and linearize the system around the equilibrium points and compute the eigenvalues to determine the stability for them. So let's assume that you are dealing with gamma. So you are now suggesting multiple values, or you are suggesting a range for gamma, and for each value of them, you are going to solve and linearize the system and compute the stability for each point. Based on these points, you will now classify what are the stability points and what are the instability points. For both of them, you will plot the bifurcation diagram, let's say something like that. Then in this case, we have this range for stability and this range for the instability or instability. Then based on that diagram, you know now what is the suitable values for gamma or the selected parameter. You can do that for other parameters to know your constraints or limitations for the given parameters. The third step is checking the stability. And checking the stability requires linearization. And to do so, you will compute the derivative dx by dt, or in general, you need to calculate the Jacobian. And the Jacobian differs if you are dealing with one-dimensional equation or two-dimensional equations. And we highlighted that in a previous lecture, comparing between them and how to calculate the Jacobian for each of them. Simply, for the 1D, you have the equation. You will apply the partial fraction according to x or the variable in hand. Based on that, you will get an equation, and you are going to substitute with the different equilibrium points or the points you have, and based on the output or the sign, you are going to determine if it's stable or unstable or neutral. If it's below 0 or negative, then it's stable. If it's above 0 or positive, it's unstable. If it's equal 0, then it's neutral. So based on these three steps, we can handle any biological model or system and understand the behavior of that system. So we are not going to cover the handy calculations here, but instead we are going to reflect that using the code. So simply go to lecture 10 lab exercise 1 hell, and you can use this code simply for different applications that got 1D system or just an equation with a single variable. And you are going to highlight again how to deal with a 2D system with two variables, and you can understand how to upgrade your code to deal with different dimensions such as 3D or 4D equations. So at the beginning of the code, we imported the necessary libraries. Then we got the model as a function by accepting the variable and calculating the result based on the given equation. And here we have the optional parameters. You can update these values or pass it during the call for that function. Also, we calculated the derivative of that equation that will help later to calculate the Jacobian. So here we got the differentiation. Simply, we have the numerator, the denominator, and using these two, because the numerator over the numerator has a specific type of differentiation, which is the numerator or the derivative of the numerator will be the denominator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator. All of that over the denominator squared. Minus, we have here gamma x, the derivative of it will be gamma. So now we have our differential equation dx by dt, and this will be the derivative of that equation which will be considered for solving the Jacobian, or this is the second derivative of our equation. Also, we created RK4 method that will accept our function, our initial condition, the time span, and the time step. Here we got our initial value, which will be x naught, and based on that we calculated or created a loop to create k1 to k4 parameters or weights, and then we used these values to calculate the next step. It will iterate from 1 until we reach the end point, and at the end we will return the vector t and the vector x. Now we are ready. We have our three ready functions to be used in our code. First, we created the different parameters such as beta and k gamma and the initial condition. We also created variables for the time span and time step, and then we created a lambda function that will be our function. Why we did that? Because each of them or each of these equations require parameters or arguments here. So simply we pass these arguments so that by injecting it into or encapsulating it into a lambda function, it will only require x, not other parameters. if you have a function that requires a set of parameters and you need only to give it a single parameter, you can simply encapsulate it into another lambda function and call the original one with the given parameters. Now we can use that function in the Roncutta 4 because the RK4 requires a function here, which is here, that will be later accept the x values here, 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 and here. The RK4, we mentioned, it will return the t and x vectors. Also, we calculated the dx values, which is the corresponding values from calling the Hill equation, which is the original one here. And we will use all of those to create a set of plots. And these plots will let us understand the behavior of our system. One will let understand the behavior of the system based on t versus x which is input, and this one will let us understand the behavior from t versus dx by dt. So we have two plots here. One is related to x and another related to dx, which is a derivative. We mentioned that we need to calculate the equilibrium points automatically based on our system. And to do so, we created a range from 0 to 100, and as these values are our initial conditions, and then we use the fsolve function to get the equilibrium point, and if that equilibrium point doesn't exist in our equilibrium points, then it will be appended to that list. So by looping on that range, we are searching for the different equilibrium points. Then we are going to print. We don't know now if the equilibrium point is stable or unstable. Then simply we will measure that based on the Jacobian. How to do so? Simply we have the derivative of our equation. Loop on the different equilibrium points, pass the value here, and get the Jacobian value. If it's below 0, it's stable. Above 0, it's unstable. Otherwise, it will be neutral. Then we printed them. Now we got our equilibrium points. Then we created a figure 2 by 2, which will be 4 subplots. These 4 subplots will let us understand the behavior of our system. The first one, as mentioned, is the time versus the concentration, or t versus x. The second one will be t versus dx. The third one is the bifurcation diagram. And we mentioned to handle a bifurcation diagram, we need to change a parameter. So here we set n by 1, and we are changing the k values from 0.1 to 15 with 500 points, and we need to know which of them is stable and which is unstable. So we created two lists here and then started to loop over the k points. We created the equilibrium points inside the k value or inside that loop. Then here we are trying to check which is stable and which is unstable based on the Jacobian value. So this value will be our Jacobian. By the end of iterating over that loop, we will get the stable and unstable points, and then we converted them to NumPy arrays. Using these points, now we can plot them in our bifurcation diagram. You can plot them as lines or as scatter points. The fourth one will be another bifurcation diagram. But instead of dealing with k, now we are changing the values of n. We set k by 1 as a constant, and it changed the n values from 1 to 10 and made the same process, but now instead of dealing with k, now we are dealing with n, then plotted the bifurcation diagram here. At the end, we saved and displayed the figure and freed up the memory from that plot. If you executed the code, you will find something like that based on these given parameters. Beta is 1, n is 1, k is 1, gamma is 1.1. You will get two equilibrium points. One is 0, one is 9. 0 is unstable and 9 is stable. And to understand the figure, the first subplot is the time versus x. So by increasing the time, the concentration increases until it reaches a certain value. And for the second subplot, which is the time versus dx by dt, or the derivative of our concentration, it increases and then decreases until it reaches a value near 0. So this means we don't have any loops here, or periodic or cycles. And regarding the stability, as you check here, we have the solid line, which will be the stable, and this one will be unstable. As you see, it's line, and you can simply make it like a scatter points to understand which point is stable and which is unstable. But from that, we can understand that the values in that area will be stable and here is unstable, and the transitioning point, which is 10, which is the merging between the stable and unstable points. If you tested it, it may go to transit from stability to instability. The same for the fourth one. Here we are changing the value for n from 1 to 10. So this is 1, this is 2, 3, 4, and so on. This is 1, this is 2, 3, 4, and so on until you reach the end. So based on these two bifurcation diagrams, you can understand and know which are your ranges for stability and the others for instability. And also from here, you can know which is a stable equilibrium point and which is not. And from this figure, you can know what is your maximum capacity and your minimum capacity. And from that one, you may understand if there are cycles or periodics, or what is the behavior according to the derivative of your concentration or your variable. This will be your corresponding MATLAB code with the same output, but instead of dealing with a line plot here, we plotted a scatter plot to understand which is stable and which is unstable. And in MATLAB, we did the same. We began by clearing and closing the figures. Then we set the parameters. We created a function, which was lambda function in Python, and executed the RK4. We calculated the corresponding dx values for plotting, and then we tried to find the equilibrium points and printed them. Then we checked the stability for each equilibrium point. Then we printed the stability of them on the window. Then we started to create the subplots t versus x, t versus dx by dt, and one for changing the k values, which is 4 with a bifurcation diagram, and another bifurcation diagram, and one by changing the n variable. This is how we created the scatter plot, and this will be the other one, which is also the scatter plot. Then we saved the figure, and at the end, we included our function. As we mentioned in MATLAB, if you need to execute a code and include functions, put them at the end of your code. Here for the equation, the derivative of it, the RK4, and again, this will be the corresponding output from MATLAB. Here, we changed the parameter k that we highlighted here. It may transit from stability in instability. And as you see, we got a neutral equilibrium point, just one equilibrium point. And as you see here, t versus x, by increasing the time, the concentration decreases. While here, the concentration increases until it reaches a specific point. So we may say that the system transited from being stable to something weird or unstable behavior from the system, or in general, you may change the parameters, and at some point you may say, this shouldn't be the behavior of the system I'm modeling. And you may reflect that by plotting the bifurcation diagram. If you did that, you may say, yes, at 10, there is a transitioning point here that led our system to be like that. And by doing so, you may exclude that point or that value from your criteria or your modeling parameters. The second example in this lecture is a 2D system, and also this system is nonlinear. This is because we have here v cubed. We have here the FHN model, which is nonlinear as mentioned. It's a two-dimensional system that describes the electrical activity of neurons, and it's a simplified version of the Alexi model, and it captures key features such as threshold-based firing, refractory periods, and oscillations. It's two equations, as noted. The first one is dV by dt. V is the membrane's potential, equals V minus V cubed over 3 minus W plus I. W is the recovery variable, and it represents slower ionic counts. I is external stimulation, and the other equation is dW by dt equals epsilon, and the epsilon is the time scale separation between fast voltage and slow recovery, multiplied by V plus A minus P multiplied by W. A and P are parameters controlling the dynamics of the recovery variable. Again, in the system, we need to simulate and analyze the system's behavior under varying parameters, focusing on equilibrium points, stability, and bifurcations. So again, we will use RK4 method to numerically solve the equations over time. This because we are dealing with nonlinear system, and this will provide us insights into how membrane potential and recovery variable dynamics evolve in neurons. Also, we will calculate the Jacobian matrix at equilibrium point. Using that, we will determine their stability, classifying them as stable nodes, unstable saddles, or other types of fixed points, such as spiral sinks or sources. Also, we will construct the bifurcation diagrams by varying the external stimulation or any other variable to understand how small changes in these parameters lead to qualitative shifts in the system behavior. Also, besides the bifurcation diagram, we are going to create a fourth subplot. Instead of two bifurcation diagrams, we will only plot one of them, and the fourth subplot will be for the vector field to know and check the trajectories of a 2D system, where they start and where they end. We mentioned that we are going to use RK4, but we described in a previous lecture how to deal with that using only one variable. What about two variables? The situation is simple. For each of them, create a different equation. How? Simply, for the first one, you will need Vn plus 1, or the next value of V. And this will require the four parameters, K1 to K4. So, simply create the variables according to this equation. And also for the second ODE function, create another four variables and another final equation, which is yn plus 1. Now, we can deal with each of them separately. And if you have a system with three equations or three variables, you will need to do a third ODE with another four K parameters and a final equation. So now you know the idea of dealing with RK. For bifurcations, we will do the same steps. We will choose a parameter, find the equilibrium points, but now by setting both equations to 0, and check the stability based on the Jacobian. And to check the stability, we will use the Jacobian as we illustrated for two-dimensional system. How? We mentioned that each row takes an equation. If we have two equations, then we will get two rows. This will be for the first equation, this will be for the second equation, as you see here, and the second as you see here. And for each column, apply partial fraction according to a specific variable. We have two variables, V and W. This will be the partial fraction for V, as you see here, and this will be the partial fraction of W, as you see here. Calculate that, you will get the Jacobian. Now we can get the eigenvalues, and based on the eigenvalues, we can determine the stability. The eigenvalues again is calculated through multiplying by the I matrix multiplied by lambda, as you see here, and subtracting both of them together. By doing so, we will get that matrix, and to get the determinant to determine the stability, you will multiply the diagonal, this one multiplied by that one, minus the other diagonal will be that one multiplied by that one, which will be here. The aim now is to substitute with the variables and parameters and obtain the lambda variable. By getting that lambda, you will get a value. By using that value, you will determine if it's stable or unstable. So go to lecture 10, lab exercise 2, FHN. This will be for any model that uses two-dimensional equations, and you will understand how to upgrade it to a 3D or 4D and so on. So simply here, we created again our model. Our model requires two equations. So here we got Z that will be unpacked into V and W, and created our two equations and returned their corresponding variables. And here we defined the parameters. The second equation should be the derivative of that one. So we created the derivative here. Also unpacked Z into V and W, and this will be our Jacobian, which is calculated in the lecture here. The third one will be RT4, two-dimensional. So here we create also a list and appended the variable, looped here, and appending each time the value of Zn into Z vector, converting it into a number array, returning T and Z. And you may wonder why we didn't create two equations as we mentioned here. Simply, I am illustrating here how to deal with that numerically or using hand calculations. But using code, it will do that automatically, because each call to the function will send a z value, and that z value will return as a correspondence to values. So the output here will be two values multiplied by dt. So these two calculations will be done in one step in Python. But using hand calculations, you need to do that one by one. Next, we created our parameters, created the initial condition, the time span, and time step. Again, we created the lambda function to encapsulate the parameters by calling that function and giving the parameters, executed the arq4, and executed to get the dz values. Based on these two, we can now plot the time versus z and the time versus dz. Next, we need to find the equilibrium points. As we have two variables, we created two inner loops and executed the solve to get the equilibrium, and then it checked if the equilibrium doesn't exist here, then it will be appended. We printed the equilibrium points, then we require to check the stability of each. We looped, created the stability vector, calculated the Jacobian and the eigenvalues simply by using the function eigenvals from numpy. Based on the eigenvalues, if all of them below 0, then it's stable. If there is imaginary only without any real, it will be periodic behavior. If it's above 0, it will be unstable. Otherwise, it will be neutral or saddle point. Then we printed that, created the figure to plot t versus v and t versus w, as we have two variables. And here we did the same, but t versus dv by dt and t versus dw by dt. Here, as a third plot, we created the phase portrait and the vector field, simply as we did in a previous lecture, to get the u and v vectors by creating a mesh grid and executing based on the given state the function to get the derivatives and appending the derivatives to u and v. Using u and v, we can now use a stream plot or quiver functions from matplotlib to plot the vector field, whether it's small arrows or a streamline. And above it, we created initial conditions, and for each initial condition, we got the solution to plot the trajectories. We plotted the trajectory, the start point, and the end point, and also we plotted the scatter points, which reflects the equilibrium points. The fourth one will be related to changing the I values to draw a bifurcation diagram. Here we changed the external value, which is I, from 0 to 2.5 with 10 numbers, and created stable and unstable vectors, looped on each point to get the equilibrium point, calculated the Jacobian and the eigenvalues to determine the stability, and by completing the iterations, we will get the stable and the unstable lists and convert them to numpy arrays using the numpy array function. Finally, because we are dealing with 2 dimensions, we created a 3D plot here and created scatter plots for the stable and the unstable. The x will be changing the parameter I, the y will be for v, and z will be for w. Finally, again, we save the figure and displayed it. By executing the code, we will get the corresponding plot. Now, let's investigate that. By increasing the time, you will see that w increases until it settles to a specific point, and v decreases from here to here, from here to here, until it settles to a certain point. And the correspondence for dv by dt and dw by dt, both of them settle at the end near 0 or at 0. And if you check the bifurcation diagram, you will see that these are the changes in the parameter I and the corresponding v and w. The blue are stable and red are unstable. So based on that, you can check which parameter or which external force will lead to a transition from stability to instability. And the output got one equilibrium point, which is stable. And the main point here in plotting the vector field or stream plot is, at each start point, such as here, here, and here, the system is going to be attracted at that point, which will be the end point for all of them. So as you see, the stream will go like that until you reach here, here, and if you are here, you may reach here, and so on. And this is your stability point. Also, you can reflect that on that figure. This will be your V value here, and this will be your W value here. So now you are combining all of them together. You can conclude here that the system is going to be stable and reach these two values at the end. And if you have different initial conditions based on the vector field and the stream plot, that all of them are going to be attracted at the point. And simply also this means whether you are initiating any values here, all of them will be rested or be stable at these 2 points. And also you can say that at external force of 0.5 you may reach instability or periodic behavior. So if you change it from I as an external force from 1.5 to 0.5, the behavior will change from being stable to unstable. As you see, the equilibrium point will be unstable. And there are a set of spikes as you see, or a periodic behavior here. Also, this will be reflected on our phase portrait or vector field, that all points are making like a loop or a periodic behavior. As you see, starting point, it will start to loop and end here, and the same for other points. It will not settle at a final value. And this will be the corresponding MATLAB plot from using 1.5, and this will be the corresponding MATLAB plot using 0.5 and as an external force. Also, it's highlighted here that all points are making a periodic behavior, and the equilibrium point is unstable. This is only because we changed the external force from a value to another value. And I'm not talking specifically about that system, it's a general idea. You can plot all of these figures, whether you're dealing with a 2D or 1D. You select the most promising or the suitable figures or subplots that will reflect the behavior of your system, and by plotting them in front of you, you will understand exactly what's the corresponding behavior of the model you are modeling or working on your project or research paper, and interpret that these ranges will be stable, these other ranges will be unstable. Using these values will lead to a periodic behavior. These values will be as stable values and suitable values. And here only we highlighted the importance of them, one for 1D system and another example for a 2D system. And regarding our problem here for stability and instability, a stable equilibrium indicates that the system will return to its state after small perturbations, and this can represent a neuron at rest or in a steady firing pattern. On the other hand, an unstable equilibrium means that any small deviations will cause the system to move away from this point, and this often leads to more complex behavior such as spiking or oscillations, as you saw in this example. And if you need to reflect that biologically, we may represent that the firing of 0.5 may correspond to the neuron firing action potential due to insufficient stabilizing forces, and this will lead to resembling spikes. And using or increasing the force or the external stimulation from 0.5 to 2.5, for example, you may encounter two stable equilibrium points, or whatever the number of stability points. We have a stable point, and that stable point means that the system settles into a stable state, reflecting a neuron that has reached a stable resting or firing state. And biologically, this could represent a neuron maintaining a consistent membrane potential or firing rate depending on the external stimuli. And also you can determine that the minimum value from the stimulation to make it in a rest state or a stable resting state should be that value by testing a set of external stimulation in your experiment. So in this lecture, we combined the different previous lectures into an example. So we dealt with solving differential equations, whether you are dealing with in an analytical or numerical manner. You are going to solve the system, and you can plot the system time versus your variable, or if you have two-dimensional or multiple dimensional system, you will plot the time versus the different variables based on your solution, whether it's analytical or numerical. We covered the bifurcation diagrams, and we mentioned that small changes may lead to transitions into stability, and we covered that into the examples. We also discussed the stability analysis, and we covered that using the Jacobian and the eigenvalues, and based on the eigenvalue you can determine if it's stable, unstable, periodic behavior, or neutral. We emphasized also how to deal with multiple dimensional system in our example, one for 1D and another for 2D, and you can propagate the idea into 3D or 4D. So by the end here, you can grab any system or any model that you have its equation and analyze the equation and capture the different ranges or limitations of the ranges to detect the stability region and instability region and interpret the behavior of that system. And you can now propagate the idea to other fields. It's not only for bioengineering, it can be propagated to other fields such as mechanical systems. And it's worth noting that it's not mandatory to deal with Python or MATLAB. It's just a programming language. You can write your own code in any language. As you know the idea, you can code it and understand the behavior. And this was the idea behind the course, understanding the behavior of systems using differential equations in different fields such as bioengineering.